All right, I think we are recording, I hope. Is that the case? All right, I think this is recording. Okay. Right, I think we are recording. Oh, I am hearing myself. Perfect. So, as I said, today we're going to do our last set of topics that I want to put on the exam. So after this, technically no new topics. But tomorrow I'll do examples and review, and also Wednesday as well. So I want to start with the Laplace transform or natural log. We said that this natural log of x has a Laplace transform by our sufficiency theorem yesterday. Last week. So we're going to see what that is. Then we'll talk about Laplace transform and integrals, and this thing called the Dirac delta function, whatever this is, and this last idea called convolution, and this little star operation. And just as an announcement, turn in everything, your homework, exam corrections, please turn it in by 8 a.m. Thursday, because homework is 30%, so please turn that in. Okay, so let's start. Okay, so first, let's talk about the Laplace transform of natural log, right? Okay, Laplace transform of natural log. Okay, now before we start, recall by the sufficiency theorem that this Laplace transform does indeed exist. So let's just recall what that says. Okay, so recall the sufficiency theorem, sufficiency theorem, which says the following. If three things are satisfied, then this function would have a Laplace transform. So what are these three things, right? So if f of x is ... one, the first condition, if said the tail is exponential order, so if f of x is all of e of kx, okay, so this is just saying that f is exponential order. This means that the function f does not grow too quickly, not greater than, it's always bounded by some exponential. Two, that the head of this function f is nicely behaved near zero. Either it is continuous at zero or the integral is finite from zero to some positive epsilon. So either f is continuous at x equal to zero, or the integral from zero to some epsilon of f of x dx is finite. And three, that the function f is nicely behaved from zero to infinity. So f is, so what that means is it's piecewise continuous, on 0 to infinity. So if these three conditions are met, then the function f will have a Laplace transform. Then Laplace transform f of x exists, right? So this is what we said last time, okay? And the function natural log of x certainly satisfies all three criteria, right? The natural log of x, it grows slower than polynomial, and so certainly grows slower than an exponential function, so it is of exponential order. The natural log of x function is not continuous at x equal to 0, but the integral from 0 to 1, it is finite, right? The integral from 0 to 1 for natural log of x is -1. So it is nicely behaved near 0. And the function natural log x from 0 to infinity is itself continuous. So it satisfies all these three properties. So by sufficiency theorem, the natural log of x does indeed have a Laplace transform. So what is this Laplace transform? Well, let me just tell you right now. The Laplace transform of natural log of x as the function of p is given by the derivative of the gamma function at 1, which is kind of weird, minus the natural log of p divided by p. O divided by P. Okay, so this is the Laplace transform of natural log of x. Okay, so we're going to see why this is true. But before we do that, let's also use our behavior theorem to see if this makes sense. Recall that if our function satisfies 1, 2, and 3, and so Laplace transform exists, then by the behavior theorem, it says that the long-term behavior of the transform will go to 0 as p goes to infinity, right? Do you remember that? So this is kind of nice because this obeys the behavior theorem, which says if a function satisfies 1, 2, 3 above, if f satisfies 1, 2, and 3, then not just the transform exists, but the limit of the transform goes to 0 as p goes to infinity. Indeed, this as p goes to infinity, this goes to 0, right? The gamma prime of 1, whatever that is a number, and natural log of p that grows slower than a polynomial and is being divided by a polynomial, just p. And this goes to 0 as p goes to infinity. So this satisfies this behavior theorem, certainly, because it's a function that satisfies these three properties. Okay? So now let's see why this is the case. So why? Question mark. All right. Now, looking at this expression, it involves the derivative of the gamma function evaluated at a number 1. So let's actually just calculate gamma derivative of gamma, okay? So this is also a good time to review what gamma is. Recall, the gamma function as a function of a, this is defined by integral, right? This is the integral from x equal to 0 to infinity of e to the minus x and x to the a minus 1 power dx. All right, so this is this indefinite integral, improper integral from 0 to infinity of this thing. And let's calculate its derivative, right? So the derivative of a, and this is the part where we're going to use a special method like last time. What is this method? This method is ignoring all the problems. What do I mean by that? Well, here's a derivative, and it's not clear why we can move this derivative into the integral, but that's what we're going to do. All right. So this is throwing caution to the wind for a moment. Now, this can all be justified, but we kind of don't care at this moment. We just say, well, let's say this is true. And it is true. So let's move the derivative inside the integral. In this case, we get x from 0 to infinity. Now, what is this? We need to differentiate with respect to a. Okay, so now e to the minus x has nothing to do with a, so that derivative passes through that. We do need to take the derivative of x to the a minus 1, though, dx, right? So what exactly is this thing? Well, remember from Math 8, hope, that if you differentiate, say, with respect to x, of a function b to the x, an exponential function, exponential functions just have derivative that equal to its own, but when the base is not e, then you have an extra factor of natural log of b, right? So this is natural log of b times b to the x, right? Remember this? Okay. So here we're differentiating a. A is in the exponent, right? So we can do this. This is e to the minus x. Now, this looks kind of bizarre, but let me write it this way. D by dA of x to the a over x dx. Again, we're differentiating with respect to a. So a is an exponent, x is the base, and the denominator x, that's doing nothing. That's just a constant with respect to this derivative. So this is x going from 0 to infinity. e to the minus x, natural log of x, right, the base, times x to the a divided by x dx. All right. Now, x to the a divided by x, of course, is x to the a minus 1, right? So now we get this thing. And what do we want? Well, here we are suggested that we should plug in the number 1, right? So let's plug in the number 1. So gamma prime of number 1 is equal to, let's see, x going from 0 to infinity, e to the minus x. I'm going to plug in 1 in the places of a, which is up here, right? And that's just x, so x divided by x, that cancels. So we just have e to the minus x times natural log of x dx. So we're halfway there. We computed gamma prime of 1. It is yet another integral, all right? Let's actually check out what this integral is, by the way. It is a number, but let's check out what this number is. So let me go to Desmos right here. All right. Let us type in this integral that we just got, which is the integral from 0 to infinity of e to the negative x times natural log of x dx. Let's see if Desmo can do it. It gave us the number, negative 0.5772, dot, 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 dot. Right? So this is the decimal answer, which is kind of neat. Let me copy this. And it is just a number. It is just a number. Okay. So let's go back. Right. So this is this number. Paste it here. Okay. Just a number. Oh, can I move it? Can I move it? Can I move it down here? Sure. This is just a number. Okay. And I'm going to put just in the quotes because this number, in fact, is very famous. And hopefully, to everybody. Okay. All right. But we're not done because we want the Laplace transform of natural log of x, right? Now, if you look at this expression of gamma prime of 1, it looks like the Laplace transform of natural log of x, except when we write down the Laplace transform of something, we're integrating e to the minus px times something. I don't have e to the minus px, I just have e to the minus x here. So what do I do here? So let me remark here, this looks almost like the Laplace transform of something, right? Except that it is not e to the minus px, it's just e to the minus x. So let me show you a trick to turn an integral where you have e to the minus x times something into a Laplace transform. And the trick is just do a substitution. Okay, so let me show you. So let's well, how do I get minus px to show up? Is just to let x equal to something like, say, pt. Let's use a different variable. I reuse x here, so let's use t. Where p is a fixed constant, let's say it's positive, so it converges, it's a fixed number, all right? And if we have this, then dx is equal to p dt, all right? So we're gonna use this to rewrite what gamma prime of 1 is. Let's see. So we have gamma prime of 1 is equal to, let's see, when x is 0, what is t? Well, when x is 0 and p is positive, then t must be 0. So we integrate from t from 0 to when x is infinity, t is infinity, t to infinity. And here we have e to the minus pt, right? So magically, I get this pt to show up. and times the natural log of x, which is pt. And dx is p dt. So now we have this new expression. Okay, so far so good. And okay, this is kind of neat. We got an extra p. This p is a constant, so I can divide it over. So we have gamma prime of 1 divided by p is equal to the integral from t going from 0 to infinity of e to the minus dt. And the natural log of the product pt, we can separate that into a sum. So that's natural log of p plus the natural log of t dt. Yeah. So far, so good. And here, this integral, we can separate into two integrals to deal with them. E to the minus pt times natural log of p plus the integral of t going from 0 to infinity, e to the minus pt, natural log of t dt. Both of these are of dt, so let me write that in. Okay. Now look at these two terms. The first term, because we're integrating with respect to t, natural log of p is just a number, so it will come out of the integral. So all we're doing is integrating t going from 0 to infinity, e to the minus pt dt. Okay. Now the second term, however, look at this. This is t going from 0 to infinity, e to the minus pt natural log of t dt. This function, this has the form of integrating. If you imagine t are actually just x's because t is a dummy variable, this really just reads integrating x from 0 to infinity, e to the minus px natural log of x dx. So the second term actually is just the Laplace transform of natural log of x. It's a function of p. Okay, so that's what this term is. And the first term, we just need to figure out what this integral is. Okay. E to the minus pt, of course, the antiderivative is e to the minus pt divided by minus p.
This is just Laplace transform of 1.
This is, yeah, that's also Laplace transform 1. So that's actually very good to recognize that. But you can, of course, evaluate this bound as well, which is 1 over p. Very good. So it's kind of nice to be able to recognize integrals as Laplace transforms, which we can just write down the answer, right? So this is 1 over p. So let me write down what you just wrote, what you just said. The integral from t from 0 to infinity of e to the minus pt dt, you can imagine there's a multiply by 1 here. So that is a Laplace transform of 1, which is 1 over p. So regardless, this integral, first integral is 1 over p. Plus the Laplace transform of natural log of x of p. So now we can just solve. So if we solve, we just need to subtract this natural log of p divided by p over, and we just get our formula, Laplace transform natural log of x as a function of p is the derivative of gamma at 1. So it's a number, this number, minus 0.5772, blah, 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 minus the natural log of p all over p. Wow. Kind of interesting. Okay. So we have this result. So I want to make a few comments. Well, firstly is that, well, regardless of whether we can calculate this Laplace transform, like actually the exact formula, we already knew some formula would exist, or this integral would exist because of our sufficiency theorem. And we also know that how it's going to behave at large p. At large p, this function, this transform will go to 0 as p goes to infinity. So we already expected all of this. Then it's just a matter of whether we can be clever and calculate what this thing is. So this is a little bit roundabout that we calculate gamma prime first to get this result. All right. Now, I do want to make a couple comments, okay? So remark, this is more like food for thought, a commentary. This number gamma prime of 1 that we just saw, I think I mentioned it before, is actually kind of famous. This is the negative of little gamma, which again, little gamma is about 0.5772 that we just calculated earlier. And this little gamma is a very famous constant. It's called the Euler-Mascheroni constant. Euler-Mascheroni constant. Sometimes children like to call it Euler-Macaroni constant, but it's the Euler-Mascheroni constant. And Euler himself calculated, I don't know, maybe like 10 places of this number. I'm not so sure. And later people try to calculate more and more of this number. And this number, we know almost nothing about. Well, not really. We do know a lot of things about them. We also don't know a lot of things about them. For example, currently, we don't know whether this is a rational number or not. So maybe instead of saying we don't know that, I would say, is gamma a rational number? Question mark. Homework. I would just say hard homework. Extra credit. Okay. All right. Well, we don't know whether it's even a rational number. But what is this number, right? So why do we care? Well, this number is actually quite geometric. So as it turns out, let me show you. If you were to graph out the curve 1 over x, which looks like this, okay, that's not, make it better. Okay, say this is a function y equals to 1 over x, and you find out where the number 1, number 2 is. Let me write them all out. 3, 4, 5, 6, like this. And what you do with this curve is this. At 1, you draw a rectangle at 1, okay, with an overhang so that it crosses to 2 like that. Let me see, a bit better. Yeah, like this. And then you keep doing this, so you create a staircase like so. Basically, this is some sort of right-hand Riemann sum of the function 1 over x. Now, the overhang part, let me shade it. This part right here, these blue nearly triangle parts, they add up and they converge, right? Because if you imagine you shove all these blue parts to the right, they are less than 1. The heights are less than 1 in total. So gamma is the total area of these blue parts. Gamma is the area of these blue wedges. And it's kind of bizarre that it shows up in this this gamma function. In fact, little gamma is actually named after big gamma function. When Euler was analyzing this Euler-Mascheroni constant, or to him, he didn't call it Euler constant, he called it the letter C. But later people rename it to little gamma because it's relation to the big gamma function. So that's just something that is interesting. This number shows up in many fields of math, more so in number theory. So it sort of has this key between gamma function and zeta function, which is the Riemann zeta function that is important in number theory. But anyways, just something for you to look up if you're interested in. I want to make another remark since we're talking about random stuff about gamma. This is just random fun fact, okay? So remark number 2, this is just a random fact about gamma. Because right now, you might think that gamma is a very unfamiliar function, right? This gamma of x. Let me write gamma like this as a function of x. So if I write it like this, let's say I change my variable to t going from 0 to infinity, e to the minus t, and t to the x minus 1 dt, like this. Now, do you remember what the graph of gamma looks like, right? So it looks something like this. On the positive part, it just looks like an asymptote at 0 and it grows really, really fast, right? And that's because on the positive part, it is trying to approximate, the factorial function. So this part right here is, approximately, x factorial. Right? It's this x factorial part, and it has a vertical asymptote at 0. And in fact, it has a bunch of more vertical asymptotes at the negative numbers. And it alternates in sign. So for example, the first piece is going to be negative, and then it's going to be positive, and then it's going to be negative and positive, like that. It alternates like that. Right? So this is the graph of gamma. And it looks very bizarre. And gamma has this property, I hope you remember, is that x times gamma of x is equal to gamma of x plus 1. So it has some recursive property about this gamma function. So we learn about this, and it looks very bizarre, right? This gamma function. Well, as it turns out, gamma is actually related to a function that you know very well, okay? That you actually see many times in your life. You just don't know it. So as it turns out, the function x over gamma of x plus 1, actually I want to write it as 1 plus x. Yeah. And times gamma of 1 minus x, this is a function you have seen before. Dot, 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 dot. Okay. Would you like to type in your guess, make some guesses what this is? All right. Do you have any guesses what this will look like? X over gamma of 1 plus x divided by gamma of 1 minus x. Well, how can we guess that, right? Well, let's see. I'm going to use decimal to plot this, all right? And we're going to see what this is, all right? Are you ready? Are you excited? Let's check it out. So first, let me define gamma. Okay, let me delete this. Let's write g of x for gamma. I think I can type gamma. No, I don't. Okay, I'll type g. The integral of from 0 to infinity of e to the negative p, e to the x minus 1 dt. Okay, so this is a gamma function. And in fact, Small also tried its very best to plot it, as you can see. And it's not quite clear. It doesn't understand how to do the negative part, but this will suffice. This part is fine. We just need a little bit. All right. So this is at least the positive part of gamma. And what I'm going to do is I'm going to do x divided by, all right, gamma of 1 plus x times gamma of 1 minus x. Are you ready? Drum roll. Let's see what it is. Calculating. Is it plotted? Ooh, it's plotted it. Let me turn the gamma off. Let's take a look at this. Do you recognize what this function is? Would you like to guess? This is sine. This is sine of x. Well, here the period is actually 2, so this is actually sine of pi x. Now, if you plot sine of pi x, well, the scaling is off, so it's actually sine of pi x divided by the pi. And let's see if it plots it. There we go. Do you see how it overlaps? Isn't that cool? Right? Now, there is some little error over here. That's because gamma, this integral, is having issue trying to calculate near these divided by 0 parts. But it is a sign of basically a sine function. So that's pretty amazing, actually. So let me grab these.
Can we try defining p of x as x minus 1 factorial? This thing does plot the complete factorial function. Like you could just shift that thing by 1.
Yeah, that's right. Yeah. But, okay, so let me copy this. Anyways, this gamma function is actually just related to sine function. So it's like, so that's why this gamma function it's pretty it's actually a very common function actually. And for a while, mathematicians wanted to just include gamma function as one of the basic functions that you should just learn, like e to the x and natural log of x. But I guess I never took off. But this is actually sine of pi x over pi. So if you're interested, you can definitely Google or Wikipedia gamma function and see a bunch of more properties of it. All right, good. So that's just something neat. Okay, so this is basically what I want to say about the Laplace transform of natural log. And let's move on to our next topic, which is Laplace transform and integrals. Right. All right. So hopefully this all makes sense. Topic number 2. Okay. So Laplace and integrals. Okay. Or rather, antiderivative. Okay. So just like how we have derivative rules, when we deal with Laplace transform and derivative, there is an inside rule and an outside rule. And similarly, with integrals or antiderivatives, we're going to have inside and outside. So we're going to see what that is, right? So first, let's recall, just remember what the derivative rules were, right? Just as a review. Okay. So do this. Okay. So recall the derivative rules. Okay. And we have 2 of them. The inside one, let me remind you, it was something like Laplace transform of f prime of x of p is equal to, and I hope you can all recite it in your sleep, it is negative f of 0 plus p times the Laplace transform of f of x of p, right? And the outside derivative rule, d by dp of the Laplace transform of f, this is equal to, well, this is equal to the Laplace transform, oh, sorry, the negative, what? The negative, there's a negative sign here, okay, be careful, of the Laplace transform of x times f of x. Okay, and the crucial observation is that here there are 2 variables, the inside variable x and outside variable p, and differentiating by x inside correspond to multiplication by p somewhere outside, right? Now there's other junk, right? But roughly speaking, differentiating inside by x correspond to multiply by p on the outside. And similarly, differentiating by p on the outside correspond to multiply by x on the inside. Do you see that? Right? And there's also some extra junk. There's like a negative sign that you want to be careful, right? And I sort of drew this little picture that says that, well, you know, in some ways that this x and p are conjugate variables, that they kind of play, you know, hand in hand in this relation, that multiplication by one is differentiation by the other. So what can we say about integration then? Well, if you were to guess, if multiplication relates to differentiation, then division will correspond to integrals, and that is indeed the case. So let me write down the 2 integral rules for you here. So for integrals, for integration, we have the following. And these are all integrals with bounds. Okay, these are not indefinite integrals, but let's write them down. So we also have inside integration and outside integration. So here's the inside one. The Laplace transform of the integral from, let's say, t going from 0 to x, all right? So this is going to end up as a function of x. We start from 0 to x of f of t dt, okay? So if I integrate this, I now get a function of x. If I compute the Laplace transform, we get a function of p. And what we're going to get is this. It's going to be 1 over p times the Laplace transform of f of x of p. So integrating on the inside by x correspond to multiplication by p on the outside, a division by p on the outside. Similarly, so let's say this is the first one. Similarly, we also have an outside integral rule. Now the outside one, you have to be careful how we're using it. We're integrating t from p to infinity, all right, of the Laplace transform of f of x as a function of p. Well, here the variable integration, I want to write it as t dt. So if you just integrate the Laplace transform of something starting from p to infinity, then what we're going to get is the Laplace transform of f of x divided by x. Okay. And again, the left side of this integral, you integrate from p to infinity. After you integrate, this should be a function of p. Right? So these are the integral rules. We have an inside one and an outside one. And it kind of parallels to the derivative rules. Instead of multiplication, we have division. Division by the variable corresponds to the integration of the other variable on the outside or inside correspondingly. Okay. Now, you do have to pay attention of where these bounds are set. So, for example, the outside rule, we start from p to infinity, and the inside rule would go from 0 to x. And so pay attention to these bounds. You could modify it to get other rules, but these are the easiest one to calculate. Okay. Now, of course, you're dying to know, why does this work, right? So why does this work? So why? And the answer is changing order of integration. Now, as it turns out, well, because Laplace transform itself is an integral, so if you do Laplace transform of integral, naturally we have a double integral. And the integral of a Laplace transform, that is also a double integral. So what we're going to do is we're going to play around with these two integrals. We're going to change the order of integration, and we're going to get these results. This is, of course, a topic in Math 11. So if this is not too familiar, it's okay. But if you have taken Math 11, that's great. Okay. I just want to quickly prove these and then give you examples of how do we use them. All right. So let me just quickly prove it. It just involves a little bit of Math 11, and let's just do it very quick. So proof of A. Okay. So let's calculate the Laplace transform of this integral. And this idea of changing order of integration is certainly something you will see or have seen in Math 11. So I'm not too sad to show you this. First, to start, whenever you deal with a Laplace transform we don't know how to deal with, we write down its definition. So this is an integral of x going from 0 to infinity of e to the minus px times the integral t going from 0 to x f of t dt, and then outside dx, right? All I did is I substituted, this into the definition of Laplace transform. Okay. Now, this is a double integral. this is t going from 0 to x and x going from 0 to infinity. This, by Fubini, you can think of a double integral. Let's write x on the outside first. X going from 0 to infinity. T going from 0 to x of e to the minus px f of t. Now, because the inner integral is with respect to t, so I'll write dt first. And the outside integral is with respect to x, I'll write dx next. So we have this integral. The idea is, what I want to do is to change the order of these two integrations. Okay? Now, naively, you might think, oh, why don't I just change it? The problem is the inner integral depends on x. And the outer integral is an integral of x. So when I change it, I cannot just move this inside to the outside because it still depends on x. When I finish with the inner integral, it should not have any, when I finish with the outside integral, it should not have any x. So if I just switch them directly without doing any work, I'm going to have an x on the outside, and that's not going to be correct. The answer has no x at the end. So we're going to analyze this very carefully. So how do we do this? Let's draw out the region to which this integral is being defined on. Okay, so let's say this variable here is t and this is x. Now, the region t going from 0 to x, it's saying that, well, for every value of x, I need to go from 0 to t, 0 to x. So it's from 0 to the 45-degree line. So right now, this integration is integrating this bottom triangle area. Okay, so the region that is being integrated currently is this region right here. That's what this double integral is suggesting. So if I want to switch the order from t to something and on the outside and x from something on the inside, I now need to change the direction of this integration horizontally. I now need to change it to this direction. Now, what this is saying is, well, t go from 0 to infinity still, because we still want to capture all the values of t. But where should x start? Well, x needs to start from the value of t, not 0, right? It starts from the line to infinity. So inside, this is t going from x going from t to infinity instead. Okay, so this is just math 11. So something you'll see in math 11. And if I do that, now I have e to the minus px f of t dx dt, like this. Now, anything that has no x's, can be moved in front of this integral like this. For example, the f of t. So I would do that. F of t times the integral x going from t to infinity of e to the minus px dx. This can be integrated dt. All right. So I got to evaluate this. Let's do it. This is not too bad. This is just calculating e to the minus px divided by minus p from x going from t, x from t to infinity dt. If I plug in x as infinity, the term e to the minus px is 0. And if I plug in x equals to t, what do I get? I get e to the minus pt divided by, not minus p, because this is being subtracted, the bottom bound, so just divided by p dt. And if you stare at this, this is just saying this is 1 over p of the integral t going from 0 to infinity of e to the minus pt f of t dt. tacitly, I assume that t is positive in order for this integral to converge. And we get this expression. The integral part should be familiar. The integral, if you read all the dummy variable t as x, that is just a Laplace transform of f of x. So, aha. Go, aha. The Laplace transform of this integral, it is just equal to 1 over p times the Laplace transform of f of x. Very cool. Yeah. So what we've shown is that by using this change of order of integration, because Laplace transform of integral is a double integral, if we change the order of integration, then we can rewrite this double integral as a new double integral, which we can recognize as just simply 1 over p times the Laplace transform of f. So that's just because after we interchange, this is something common in Math 11, that once you interchange the order, then suddenly you can integrate it, parts of it easily, which is what happens here. Okay. Long story short, we have proved A. Laplace transform of integral is 1 over p times the Laplace transform. Now, of course, watch out for the details here. So let me show you a quick example of this rule right here. Okay. Example usage. Okay. Well, let's calculate the Laplace transform of, say, the integral of t going from 0 to x of sine of t dt. Okay. So let's see what we should get, okay, by using this rule. So the rule says if you're doing the Laplace transform of an integral from 0 to x of the function, right, like this, then we should just write down, we can just directly write down 1 over p of the Laplace transform of the function. The integral comes out and just get 1 over p. But you have to be careful, is the bound from 0 to x? Let's see. Our bound, yes, it is from 0 to x. Okay. So by theorem A, you know, this is just 1 over p times the Laplace transform of sine of x as a function of p. Now, do you remember what is the Laplace transform of sine of x? Maybe you can put in the chat. But to remind you, the Laplace transform of sine of x is 1 over p squared plus 1, right? This is 1 over p squared plus 1. So the answer to this is just 1 over p times 1 over p squared plus 1. Done. Now, you say, wait a second. Okay, that's great. But isn't the integral of sine some kind of cosine, right? But cosine, isn't cosine p over p squared plus 1? Like what? It doesn't quite look like that, right? Well, let's do it carefully. So let's check. We can actually calculate this antiderivative out exactly. But remember, this is a definite integral, so we gotta do it carefully. There are bounds to consider. You cannot just say, oh, this is the integral of sine is just cosine. Well, let's see what it is. The antiderivative of sine is indeed minus cosine, right? But you gotta evaluate from 0 to x, like that. Well, let's see. So this is saying that this is a Laplace transform of, when I plug in x, I get minus cosine of x, right? And then minus, when I plug in 0, what's cosine of 0? Cosine of 0 is 1. So minus 1, so we're going to subtract 1. So we have this. So what we're really calculating is the Laplace transform of minus cosine of x plus 1. Okay. We know how to compute the Laplace transform each of these functions. So let's write them out. The Laplace transform minus cosine is what? It is negative p over p squared plus 1. This is the Laplace transform minus cosine. And the Laplace transform of 1, as you know, is 1 over p. So is this the same result as this? Well, let's figure it out. Here we have two fractions. Of course, we can put it together. Let's put it together. Finding the common denominator, it is p times p squared plus 1, like so. And the first fraction, the numerator, I need to multiply by p to get this common denominator, so I have minus p squared. And the second numerator, I need to multiply by p squared plus 1. So I have minus p squared plus p squared plus 1 divided by p times p squared plus 1, which gives me indeed 1 over p times p squared plus 1. Check. Right? That is exactly what we expect by this integral rule. All right. So in some sense, we calculated this without calculating an integral, which is kind of neat. Right. So don't get, tripped up by this. So isn't it neat? Yeah. Cool. All right. So these are the same. Let me just remark. Same.
What if the bounds were not like the ones on this theorem? Like, would it mean not to use definition?
Then it's a little bit tricky. Then you have to rederive these integral rules. So it's not very clear. So you want to make sure that it is from 0 to x. Yeah, that's all I will say. Okay, yeah. If it's not from 0 to x, then you're going to have extra factors. So you might have to integrate that out first, and then or separate that out so that so part of it looks like 0 to x. Then you have to deal with the other integrals separately, like directly. You have to integrate it out before you do anything. So there's no general rule that I can think of right now. Okay.
Okay.
Yeah. Okay. So just be careful when you use these rules. Just double check. Okay. So let's say we have this. Then you say, okay, we're still on rule A, by the way. We haven't gotten to rule B. How else can I use rule A, right? So I want to introduce a very important type of question, which is a cousin to differential equation called integral differential equations. So let me put a star here, okay? This is an important application. Okay, of rule A is that it can be used to deal with something called integral differential equation. Let me explain what this is. Can deal with integral, sometimes people write integral differential equations, or sometimes for short, it's just integral equations. Okay, and just like differential equation, it is an equation with derivatives. Integral differential equation or integral equations are equations with integrals instead for an unknown function y. So let me give you an example of this, and we'll see why we can use this. So example. Okay. So say our task is the following. Find a function y, let me write little y of x, such that it satisfies the following. That little y of x is equal to x plus the integral t going from 0 to x of y of t dt, like this. Okay, so this is an example of an integral equation. We don't know what y is, and if anything, it says that y is equal to something plus the integral of y, or integral y times something, right? Just a simple situation. Now notice the bound here is already in from 0 to x. And this is why, I'm not too dissatisfied with this R rule from 0 to x, is because this is the prime situation where we're using this. That this is saying that starting from initial time t equal to 0, we have some condition like this. So this is used in this case, really, this rule. So how might we solve this using this rule, right? So what we'll do is to apply Laplace transform to both sides. In orange. Okay. And just per our tradition, we'll write big capital letter Y as the Laplace transform of little y. Okay. So that's our tradition. So if I apply Laplace to both sides, let's see what happens. This little y, that turns into big Y. Okay, that's how we convert. Okay, so this becomes big Y. Little x, the Laplace transform of little x is what? It's 1 over p squared. Okay, 1 over p squared. Okay. Plus, now we're gonna take the Laplace transform of this integral right here. Ah, that's great. This is of the form t going from 0 to x, a little y of t dt as a function of p. We know how to deal with this. Using our first integral rule with Laplace transform. In this form, if it's from 0 to x of integral of f of t, it just gives you 1 over p times the Laplace transform of f. So this part right here just turns into 1 over p times y, big Y. Hence, we'll have this algebraic equation, y equals to 1 over p squared plus 1 over p times big Y. You see. And so now what we want is to solve for y as a function of p. Okay, that's not too bad. I subtract 1 over p over, so we have 1 minus 1 over p times big Y is 1 over p squared. So big Y is equal to 1 over p squared times 1 over 1 minus 1 over p. Okay, looks crazy, but not really. When I see so much fractions I don't like, I just clear the fraction. I multiply top and bottom by p. So I get 1 over p times p over p minus 1, which one of the p's cancels. So we get 1 over p times p minus 1. So that is big Y. Can we see that? Yeah. Okay. So now comes the task of figuring out what little y transforms to this. Now notice this big Y is a rational function. So in principle, I can write them out as something like a over p plus b over p minus 1, right? By partial fraction decomposition.
We could also use the reverse of theorem A.
You can also use that, but let's just practice partial fraction, yeah. And what will partial fraction say? Let's see. Right, this is 1 over p of e to, yeah. But let's just use partial fraction. Well, so yeah, there's many ways to deal with this, right? But in general, if you have a rational function, we can PFD. So this says a times p minus 1. Okay, so I will show your way as well. But let's do it first in partial fractions. A times p minus 1 plus bp, that ought to equal to the numerator, which is equal to 1. And here, this is a simple one. We can just plug in some values of p to figure out what a and b are. So for example, if p equals to 1, then then we get what? We get b is equal to 1. And if we plug in p equal to 0, then minus a minus a is equal to 1. So a is negative 1. So this tells me that this is negative 1 over p, orange, negative 1 over p plus 1 over p minus 1. That is big Y, right? And now to figure out what converts into each of these, well, little y of x then equals. So what becomes minus 1 over p? That is going to be negative 1. And 1 over p minus 1, that is e to the what? E to the x, right? E to the x. So we just have this, right? So notice there is nothing to substitute because here secretly an integral equation secretly is a initial value question as well because it includes a situation t equal to 0. So this is secretly an initial value problem. So at the end of the day, we get a specific answer without any parameters. We solve a very specific initial value problem. So we get this, right? So this is the solution right here. Now you mentioned that there is another way. So let's actually do the alternate way to figure this out. Now this is because this situation is kind of special. This y is of the form 1 over p times something. So notice that y is equal to 1 over p times 1 over p minus 1. And, well, let me first figure out what is the Laplace transform of p minus 1 is. That is a Laplace transform of, as we know, e to the x, right? Like so. So by our rule A right here, whenever we have 1 over p, we can use the reverse as you suggest. So let's actually do that. So this is saying that we need to take the Laplace transform of the integral of f of x, okay, from 0 to x. So let's see if we can do that. So we're doing this in reverse. This is the Laplace transform of integral t going from 0 to x of e to the t dt. Okay. Now this is the Laplace transform of, let's see. Well, e to the t, the antiderivative is very easy, just e to the t, evaluated from 0 to x. This is the Laplace transform of e to the x minus 1, right? No, minus 1, yes. Okay. Of p. And immediately we see we have the answer, right? Because y is equal to the Laplace transform e to the x minus 1. So therefore, little y that transforms to y, big Y, is e to the x minus 1, which is exactly what we got. So again, multiple ways to do the same thing. But this is kind of lucky. It's because our big Y has the form 1 over p times something, which of course we can use the reverse of A. So here we used A in reverse. Okay. Does that make sense? Yeah. So many ways to do the same thing. All right. Good. Okay. So this is rule 1. Okay. The Laplace transform of the integral of something inside the Laplace transform. Its main use is in this integral equation. So whenever you have an equation trying to figure out from unknown function y, but this y is also buried inside the integral, we can use this Laplace transform to sort of rescue it and rewrite it in some nice way. Okay. So that's kind of neat. Now, let's look at rule 2, part B. The integral of the Laplace transform, right? Now, notice that the bound gets even more bizarre is from p to infinity. This is so that the result can be nicely written. If it's not this bound, then it's not clear what this is. We really wanted to go to infinity though, because most of the time the Laplace transform of a nice function dies out to 0. So this would make sense in those cases. So maybe I should caveat that these rule really only works when the integral exists. If they don't, of course, then these, of course, make no sense whatsoever. So let's see how the second rule works and why that is true. Let's prove that. So this is saying that integral from p to infinity of the Laplace transform is just a Laplace transform of the function divided by x. So let's do that. Proof of B. Okay. So we want to show that the integral from p to infinity of the Laplace transform of a function of t, because that's the dummy variable this time, dt, is equal to question mark Laplace transform of f of x over x. Okay. So in the first proof, the trick was to change the order of integration. The second proof is also changing the order of integration because, again, this is a double integral. So we're going to do just that. Okay. So let's see. Just again, this is math 11, so just kind of listen to it if it makes sense. One day this will make sense. T going from p to infinity times Laplace transform f, which is x going from 0 to infinity, e to the minus px, f of x, dx, dt. Okay, so again, I just substituted the definition of the Laplace transform of f. Oh, I already made a mistake. And someone told me what is kind of wrong in this parenthesis right here. Something is not quite right in this parenthesis. Do you spot it? There's a letter that shouldn't be there, and it should be another letter. What is that?
It should have x should be something else in the f of x dx.
Not quite. Is this t right here? Do you see? That t should be the p part. So this is not p here. This is a t here. Okay? Because we're integrating the Laplace transform, and we say that the dummy variable is t with respect to t, and so we're integrating. This letter is t here. X is being integrated out. Yeah. So this is t right here. Do we all see? Yeah, I hope. Okay, so be careful. Okay. So what is this? What is this? Now the result, of course, is a function of p. That's because we end up with a p right here. This integral is a double integral. T going from p to infinity. Well, I don't know why I'm writing out again, but it's okay. X going from 0 to infinity, e to the minus tx, f of x dx, dt. And this is this double integral. Let me draw the region out again for this. The region, say this axis is t, the horizontal is x. Let's see what we want. What this is saying is for each value of t, we want to integrate all the x's. X has from 0 to infinity, has no restriction whatsoever. It's going this direction. Okay. And for which t do we start? We start from p. So let's say this is p. We start integrating, at t equals to p, and then for each t, x going from 0 to infinity. So the region is this big region right here. It's just a rectangular infinite, well, this upper infinite region right here. Okay. Okay, it keeps going. All right. Starting from p. Now to interchange this, if we interchange this, if I interchange, well, x is now on the outside. Now x is going from 0 to infinity, but because this is considered a rectangular region, so we can actually just directly interchange the integral without any loss, right? Because imagine for each x value, t just go from p to infinity, going vertically up, right? So there's nothing bizarre like the first one. So I can just interchange this because these are just rectangular region. And here we have e to the minus tx, f of x, dt, dx. So here again, I change the order. And now just remark, math 11. Okay. So now how do I integrate this? Well, in the inner integral, anything that has nothing to do with t can move outside of the inner integral, which is this f of x. And then here we have t going from p to infinity of e to the minus tx dt. Let's integrate that, dx. Now, notice the bound is from p, so we got to be careful. The antiderivative of e to the minus t, of course, is e to the minus tx all over, well, all over what? All over minus x, right? Because t is the variable being integrated. Evaluated from t going from p to infinity, dx. Okay. So this is f of x times, when t is infinity, this number is 0. And because x is positive, so it goes to 0. Minus when t is at p. So it's minus e to the minus px divided by x. Right? The minus double negative cancels because we're subtracting the lower bound, dx. And if you stare at this for a few moments, you'll realize we're just integrating e to the minus px of f of x over x, just rewriting, reordering some of these letters, which indeed is just the Laplace transform of f of x over x. Wow. Okay. So again, with a little bit of Math 11 magic, we get this. So let's see an example using this. Okay, so this is the Laplace transform of so the integral of some Laplace transform. Okay. So let's see an example. Here's an example, and typically this example is used backwards. So for example, let's say we want to find the Laplace transform of something bizarre. Let's say, how about sine of x over x? Okay. Now, when you encounter this, you say, well, we know how to calculate the Laplace transform of sine, but what about sine of x over x? Well, you say, wait a second. This has this form, a function over x, that we want its Laplace transform. So by using this rule, the Laplace transform of a function over x is just the integral of some Laplace transform. But this integral starts from p to infinity. So using rule B, this is equal to the integral of t going from p to infinity, which is the bound, of the Laplace transform of sine of x. Okay, so we're just using this outside integral rule backwards. Okay, now what is this? Well, this is the integral from p to infinity of t going for t from p to infinity of sine of x, its transform is again 1 over p squared plus 1 dp. Okay. And in the chat, you can type in, do you recognize what's the antiderivative of 1 over p squared plus 1? Wonder if we recognize this one from Math 8. So hopefully you do. This is one of the, yeah, this is arctangent, exactly. So this is arctangent of p. And we want to integrate, wait a second. So, oops, I wrote something wrong. I want to write a dummy variable here, dt, so I don't make a mistake. So here I ought to write t squared plus 1 dt. All right. And t valuing from p to infinity. Okay. Now, let's think what these are. The arctangent function, if we were to graph it, has, of course, horizontal asymptotes at pi over 2 and minus pi over 2. Okay. It is an odd function. Oops, can I draw better? And it looks something like this, right? This is arctangent. Right? So at infinity, arctangent at infinity is really just pi over 2. That's the limit, that is. Minus arctangent of p. So there we go. This is the Laplace transform of sine x over x. Now sine x over x near 0, the limit goes to 1, so it's actually well behaved. Near 0, it is of exponential order. And in between 0 to infinity, this is piecewise continuous. It's continuous. So its Laplace transform exists. It is this function, pi over 2 minus arctangent of p. And notice that as p goes to infinity, arctangent of p also go to pi over 2. So as p goes to infinity, this goes to 0, which, satisfy our behavior theorem, which is kind of interesting. But here we go. We can calculate some bizarre Laplace transforms. Okay. Does that make sense? Let's just see another example just to round out what we learned. Let's say I want to calculate the Laplace transform of the antiderivative, or rather the integral of t going from 0 to x of natural log of t dt. Okay. Now, if exams have taught you and homework, you should know the antiderivative of natural log of t. But here we can actually use one of the integral rules. Should I use rule A, the inside derivative rule, inside integral rule, or rule B, the outside integral rule? Which one should I use? I should use, I could use the inside integral rule, right? So by the inside integral rule, right here, just to remind you, when the bound is from 0 to x, this just turns into 1 over p times the Laplace transform. So the bound is from 0 to x. So by rule A, this is just 1 over p times the Laplace transform of natural log of x of p. Do we all remember what natural log of x transform is? Don't know if you remember, but it is this weird function, gamma prime of 1 minus natural log of p, all divided by p. Okay, so we just use what we just learned earlier. Right? Okay. All right. So these are the integral rules. And again, the integral rules mimic the differential derivative rules for Laplace transform, that integrating of one variable corresponds to division by the other variable on the other side. Okay. So it's parallel to the derivative rules. Okay. Are there any questions so far? I know I've been just talking, but are there any questions so far? Okay, if not, we can also leave it at the end. So right now, let's take a 10-minute break till 9:35, and then we'll continue. All right. So let's take a break for the time till 9:35. All right. All right. And then we'll come back. And we'll come back. We're gonna talk about these two new objects. One is called the direct delta function, and the other thing called the convolution. So, all right, take a break. All right, let's continue. And just to remind you, all your work are due by Thursday at 8 a.m. Okay, so please turn them in. It's a chunk of your grade. Don't want to lose points just for no reason. So make sure you turn in all your homework and your test corrections. All right? All right. So let's continue with what we're about to talk about. So first, let's talk about this thing called the Dirac delta function. All right. So let's talk about that. Now, the delta function, the word function ought to be in quotes because it's not quite something, it's not really a function per se, but it's something of a generalized function. It's a function where it has an integral, and maybe you can even define what a derivative is, but it's not actually a function. So sort of just the word function. So strictly speaking, this is not going to be a function. So technically not a function. Okay. But rather something called a distribution. So that's one, in probability, this is what we will call it in quotes. And this distribution is something that can be integrated. Can be integrated. Or sometimes people also call it as a generalized function or a generalized function. Just various names just to indicate that this is not really a function per se. But this delta of x has behaviors of a function when it's in an integral or multiplied to something else, and you'll see what that is. So let me define what this quote-unquote function or not a function is. All right, so it's kind of bizarre, this object, delta of x. So we're going to define delta of x to be the following. Okay, so we're defining it by writing down what kind of properties this delta of x would have. All right, and sometimes people will say this delta of x is something called a unit impulse. Unit impulse, and I'll explain what this means. So, what are some properties of this function? Well, if we want to think about it as a function, then perhaps we can try to write out what delta of x is if we plug in some values. So delta of x, how we're going to define it is, first of all, it is 0 if x is not equal to 0. Okay, so that's interesting. So it's basically 0 everywhere. But what happens at 0? Well, at 0, it is quote unquote infinity. Okay, so this is this weird function where it's 0 everywhere and infinity, quote unquote, at 0. It's not actually at infinity, but it has the behavior of something that's infinite. Now, the reason to be made clear later. But if you were to try to plot this, okay, it's kind of like this. It's a function where it's 0 everywhere. Okay, so it's 0 everywhere. Let me try to draw it. So it's trying to be 0 everywhere. And at 0, this is delta of x, it is suddenly this infinite spike right here. There's a spike. And then it's 0 everywhere later. Okay. So it just says 0, infinity, and then 0, like this. What's the better way to think about this is really it's a limit of a sequence of functions. So if you imagine one of these bell curve function like this, okay, let me try to make it more symmetric. And imagine that this function gets skinnier and skinnier, but taller and taller, like this. then its limit converges to something, and we say that that limit is this delta function, okay? So you can think of this direct delta function as something that is basically zero everywhere with a skinny spike in the middle, okay? So something like this. All right, okay. Now, why is this kind of a function? Well, and what does it mean that it's infinity at x equal to 0? It's kind of bizarre, right? Well, the idea is we can integrate this function. And we define the integral for x going from negative infinity to infinity. Now, most of the time, this function is 0. So it's mostly going to give us 0, but because there's an infinite spike, there's something at 0. And how much of that? Well, it's not infinite, but rather the total area, shall we say, is defined to be the number 1. Okay, so this is why it's called a unit impulse. You can imagine that this is a function that is 0 everywhere, but at 0, it has some area of 1 underneath this infinite tall spike. Okay, and because the width of the spike is 0, so the height needs to be at infinity, but it has this area, quote unquote, of 1 underneath it. So it's kind of a bizarre function. But these are the defining property of this delta. Okay, so it's 0 everywhere. At 0, the height is infinite, but its mass, its area is 1. It's a finite number. It's 1. So it's called a unit impulse. That this is you concentrate an area of 1 at one point at this x equal to 0 point. It's kind of bizarre. So what is this for, right? Well, you can use a delta function as a value picker for a function. So what do I mean by that? Let's say you take another function, say f of x, and you integrate it against delta of x. Okay, so you multiply them together. I put a dot here, that's just multiplication, dx. So what do we get here? Well, because the delta function is 0 everywhere, this function is going to be ignored everywhere except at x equal to 0. And x equal to 0, we have a total mass of 1. That 1 is going to be multiplied by f of x at 0. So we'll define this value of this integral to be f of 0, just the value of f at 0. That is the effect of integrating a function against this delta function. Okay? So if you multiply a function by the delta function, delta of x, integrate from minus infinity to infinity, you just simply pick out the value f of 0. Okay? So the integral is very easy. Okay? So these three properties defines delta. Kind of bizarre. All right. Now we can also work with translated versions of delta. Translated version of delta. So, for example, let's say we have delta of x minus a. All right. And with our loss, oh well, here we don't have to assume what a is, but what is this? This is just 0 everywhere if x is not equal to a, and quote unquote infinity if x equals to a. But it's not really infinite because it has finite area underneath this curve. So what is the area? Well, if we were to integrate minus infinity to infinity of just simply delta x minus a dx, you will get 1 still. Okay. Now, what if I integrate this function against the function f of x? If I were to integrate x going from minus infinity to infinity of f of x times delta of x minus a dx, because this impulse is set at x equals to a, so it will pick out the value of f at a. So this is just the value of f at a, simply as that. Okay, so this delta function, you can think of it as it's a function that when you integrate against another function, it picks out the value at a if it's integrating against delta of x minus a. You're just doing substitution. Now we can be even more specific. Let's say we integrate, say from x1 to x2, okay? And we integrate this function f of x against delta x minus a dx. Now what is going to happen? Well, this delta function is going to help us pick out the value at x equals to a when you integrate it like this. But if our interval from x1 to x2 does not contain a, then it's just going to be 0. But if it does contain a, then it will just be the substitution. So here we're going to define this to be the following, that this is f of a if the value a is inside the interval x1 to x2, right? So then the spike is being integrated from x1 to x2. But if a is outside this interval, if the spike is outside of this interval, then delta is just always 0. So this integral would just be 0 otherwise. Okay. So these are the behaviors of this delta function. Okay. So again, this is considered as a unit impulse because you can think of it as something that has nothing happening, and then suddenly at time equal to 0, there's a hammer, that strikes down, that strikes down at time equal to 0. But when you strike down something, there's also a finite amount of force. So some finite amount of force is being applied to it at time equal to 0, and then immediately, because that time interval is so tiny, so then it is 0 again. So just only at that moment at 0, some hammer, hit down something, create a force, and inject some force into the system, and then suddenly it stops very quickly, right? But then some energy is transferred into the system already, right? At this moment, x equal to 0. Or if you consider delta x minus a, it is at the moment of x equals to a. Okay. Does that make sense? Okay. Okay. So let's pretend we believe this thing is a thing. Again, it's not really a function. It's a distribution or a generalized function that it has these properties. It can be integrated, and it can be integrated against other functions. That's what it's supposed to do. Okay. Now, this is a weird function, but what we now like to think and ask is, well, can we calculate the Laplace transform of this delta function? Okay, so let's answer that question. What is the Laplace transform of delta x as a function of p? Now, this is a well-defined question because when we compute Laplace transform, again, it's an integral. So we're going to be integrating the some integral of the delta function, right? And hopefully I'm writing this delta clearly enough, okay? So this is delta, the lowercase of this big delta, okay? This is delta, all right? I hope that is clear. This is not f or s, this is delta. Well, what is this? Let's calculate. This is equal to the integral of x going from 0 to infinity of e to the minus px delta of x, right? dx. Okay. Now, because 0, the spike of delta of x is at x equal to 0, which is inside our interval 0 to infinity. So by our rule of our delta function is that if the spike is there, then the integral is just evaluating the function at, in this case, x equal to 0. So this is just evaluation of e to the minus px at x equal to 0. So just plug in 0 here. Wait a second. What is e to the minus p times 0? What's e to the 0? E to the 0 is 1. Whoa. Earlier, we were wondering what kind of function has a Laplace transform of 1 of a constant It turns out is this delta function. I have to create this gadget called the delta function. So here we have the Laplace transform of delta of x of p is actually the constant function 1. Okay. And we can also work backwards. So for example, for what function would you say f of x such that the Laplace transform of f of x is, let's say, our favorite number 7. So what kind of function will have a Laplace transform of 7? What do you think? Well, 7 is 7 times what? 7 times 1, right? So, and 1 comes from delta. So 7 comes from how many deltas? 7 deltas, right? Okay. So this is just a weird gadget to capture what kind of function would transform to these constants. Okay. Now, what's the meaning of 7 times delta of x? Well,
Could it be a shifted form of like delta x minus something?
well, we can do the shift. Hold on. First of all, what is 7 times delta of x? Well, delta of x itself is a unit impulse. It is the sense that at some x equal to 0, you inject 1 unit of force. The total area is 1 here. So this hammer is hitting something at this instantaneous moment, injecting 1 unit of stuff into the system. 7 delta of x is just injecting 7 units of force at x equal to 0. So this is interpreted as an impulse at x equal to 0 with 7 units of whatever force or energy or whatever you like to think about in this particular situation. Okay, so just 7 times. So the integral 7 delta x from minus infinity to infinity will be 7. Right? This is a thing that has 7 total area of stuff. Okay. Now, you could also, of course, calculate the shift of the Laplace transform of the delta by a. So let's also calculate that. What is the Laplace transform of delta of, say, x minus a? Okay. And here I'm going to assume that a is positive. All right. So what would this be? All right. Okay, so let's calculate this. Well, this equal to x going from 0 to infinity of e to the minus px delta of x minus a, right? dx. Now, this time, the spike is at x equals to a, so we're picking out the value at x equals a. Now, because a is in interval 0 to infinity, well, we assume that a is positive, so a is inside this interval. So therefore, this is just substituting a into e to the minus px. So this is just e to the minus pa. Okay. So just a explanation by itself here. That's the Laplace transform of delta of x minus a.
Professor,
Mm-hmm.
does this implies that so this also equals to the Laplace transform of e to the minus pa delta x, which means that does it true that one result of the Laplace transform could be from 2 functions? I mean, 2 functions, does it generally is it possible that they could result in the same Laplace transform?
It's possible, but we're gonna ignore that. Let's not think
okay.
about that. Yeah, let's just never think about that. So for all intents purposes, there's always an obvious function that transforms to these. Okay. Yeah. So that's fine. So you'll see when we're gonna use it. Okay. So the idea is quite often we're gonna see when we're gonna need this delta function. All right. You'll see. Okay. Of course, the application being differential equations. Yeah. Okay. So let's actually use that as our gateway to see how we can apply this. All right. So let's look at this example, and I'm going to do 3 examples, and we're going to see how this changes the solution each time. Okay. So let's do some 3 examples. Okay. Let's see, do I have enough space? Okay. Well, we're going to do example 1, 2, and 3. They're all going to look similar, but they're slightly different. Okay, just pay attention, watch carefully. So the first one is this initial value problem. Y prime plus y equal to 0, okay? And y of 0 equal to 1. Okay, very simple initial value problem. All right. The second question that I want to discuss is y prime plus y equal to not 0, but delta of x. Sorry. And y of 0 is equal to 1. All right. So same initial condition, but the non-homogeneous part is now delta of x. Kind of interesting. And a third problem that I want to consider is y prime plus y is instead delta of x minus, let's say x minus is the matter, let's say x minus 2, okay? And this is y of 0 is equal to 1. Okay. So how do each of these differ, right? So here we have 3 differential equations. We're looking for a function y. They all have the same initial value. They all start from y of 0 equals to 1, okay? But the non-homogeneous part, or the right-hand side of the equation, are all the same. The first one is actually homogeneous. It is just 0, and we let the system run. Number 2 is that instead of setting equal to 0, initially at x equal to 0, some hammer hits down and inject 1 unit of stuff, energy, impulse, force, whatever this y may be, into the system. And situation 3 is that, well, we have same system, the same initial value. Initially, it's 0 because, when x is 0, this delta of x minus 2 is 0. But at time x equals to 2, we inject 1 unit of stuff into the system. Does that make sense? So this is somehow, we can sort of, it mimics, say you have a electrical system and suddenly you inject some amount of energy into your system, or you have a spring and suddenly you pull down on the spring at an instantaneous moment. So this is where this delta could be used. And this delta of x basically tells us that, well, at what precise moment we inject what amount of stuff into the system. Does that make sense? Well, let's try to solve each of them. Okay, let's try to solve each of them. I will solve it horizontally. Let's see if I can do that. So the first case, all right, this one is easy, right? This one we could have done by either exam 1 or exam 2, but by the technology of exam 2, we write down the auxiliary equation, r plus 1 equal to 0, so r is equal to -1. So we know that the solution, because it's homogeneous, is of the form c e to the minus x, right? And because y of 0 is equal to 1, we plug in 0, we see that c is equal to, if I do that, c is equal to 1, right? Because y of 0, this is c e to the 0 equals to 1. So the solution is y of x equal to e to the minus x. Okay? That's his first problem, which is a simple exam 1/exam 2 question. Let's look at the next one. Now we have this with a delta. Unfortunately, with this delta, it's not quite clear how we could use our method to solve. So this is a special situation which shows up in engineering where we kind of have to use Laplace transform, or rather, Laplace transform is the best tool to study this type of behavior because technically this delta is not really a function. So we should apply Laplace transform here when we see such a gadget right here. So let me do that. Leave some space here, okay. So for situation 2, let's apply Laplace transform. And by our tradition, we're going to write big letter Y as the Laplace transform of little y. Okay. So applying Laplace transform to the differential equation, we get y prime, which becomes negative little y of 0 plus p times big Y, plus the Laplace transform of little y, which is just big Y, equals to the Laplace transform of delta x. Well, what's the Laplace transform of delta x? Laplace transform of delta x is 1. So we're going to put down 1 here. Now y of 0 is 1, so this then becomes, let me write it here, negative 1 plus py plus y, so that's p plus 1 times big Y is equal to 1, or in other words, big Y is equal to 2 over p plus 1, right? Now, let's think. What kind of function transformed to 2 over p plus 1? Can you think of one? Y of x is 2 times e to the negative x, right? So here, this is the solution. Now, let's think about the difference between this one and the first one. In fact, they can kind of be related because in this one, even though our initial value, y of 0 is 1, but we set the system to have an impulse of a driving force, remember this driving force term of delta x. What does that mean? That means at time x equal to 0, we inject 1 unit of stuff into it. So it is as if my initial condition is y of 0 equals to how much? Equals to 2, do you see? So if you actually solve example 1, but instead of y of 0 equals to 2, you would have gotten this solution, right? Because if y of 0 equals to 2, then c will equal to 2, and then you will get 2 times e to the minus x. So that's kind of curious, right? So here, this delta x is saying that at time x equal to 0, we also add 1 unit of stuff to y, right? So it is kind of like saying that the initial value is kind of like 2. But it's not quite clear. Not all the time it's like this, because this is y prime plus 1. What if it's y double prime? So it's not quite clear what that actual amount is. It just happens to match up with y of 0 equals to 2, okay? But that's the idea, that something is added at time x equal to 0. And that's the effect. So both example 1 and example 2 gave us this exponential decay. It's just that one of them start at time x equals 0, it starts at 1, and the second one it starts at 2, because some amount of energy or force is being added at x equals 0. Does that make sense? Okay. So if I were to plot them, the first one just decays like this. Oops, let me draw better. Right. Here, for example, 2, it starts on a higher point and decays. Okay. So that's because something's being added at x equal to 0. Okay. All right. Again, it's not quite clear how much is being added. It's just some amount. Okay. I just want to make that clear. Now, for example 3. Now, how can we interpret the system using what we just said? Well, this is kind of like the same problem. Initially, the function starts at 1. So, and at time x equal to 0, the delta function of x minus 2 is 0. So it should behave similarly as example 1, at least initially, until x equals to 2. Something happens at x equals to 2. So some amount of energy is going to be injected into it, and then it's going to decay again. So let's see how we can just solve it using Laplace transform. So again, let's apply Laplace transform. We get minus little y of 0 plus p of big Y. Again, we were writing, big Y as the Laplace transform of little y, as our tradition, plus the Laplace transform of little y, which is just big Y, equals to the Laplace transform of delta of x minus 2. Well, Laplace transform of delta x minus 2 is e to the negative 2p. Okay. And also this clarifies why we only care about a being greater than 0, because we really only care about this impulse being injected into the system at some positive time after t equal to 0. Okay, so let's solve for this. Well, y of 0 is 1, so this system becomes p plus 1 times big Y is equal to 1 plus e to the minus 2p. And this is saying that big Y is equal to 1 over p plus 1 plus e to the minus 2p over p plus 1. Okay. Okay. Now, what transform to these? Well, let me continue writing equal sign. The first one, let's see if you can try it in the chat. What function transforms to 1 over p plus 1? Do you remember? This is going to be e to the, do you remember? E to the negative x. Okay, that's e to the negative x. Now, the second function, this is kind of bizarre, but it's not completely bizarre. This is e to the negative 2p times the Laplace transform of e to the minus x, because this is just e to the minus 2p times 1 over p plus 1, right? So I can first rewrite it like this: e to the minus 2p times the Laplace transform e to the minus x. Now, do you remember something that we talked about last week? What is this? This is, to resolve this, we're multiplying the Laplace transform by an exponential on the outside. So do you remember what this becomes? Do people remember? Anyone? This is the exponential shift rule, right? So this becomes plus, just remind you on the side, the exponential shift rule. What does it say? When you have e to the minus ap, right? When a is positive, times the Laplace transform of f of x of p, this is equal to the Laplace transform of f of x minus a times the unit step function u of x minus a. Yeah. Do you remember this? Okay. So this is exponential shift rule on the outside slash translation rule. Okay. So we have this is the Laplace transform of e to the minus quantity x minus 2 times u of x minus 2 of p. So the result is that little y of x is just e to the minus x plus e to the minus quantity x minus 2 times the unit step function x minus 2, like this. Now, one could write this as a piecewise function, which one should try. But what does this function look like, right? This is saying that the solution, y of x, initially looks like e to the minus x. And then at time x equals to 2, do you remember how to interpret this? This is saying that something got turned on at x equals to 2, right? The function of e to the minus x minus 2, which is really e to the minus x translated to the right by 2 units. So the graph of this looks something like this. This has this graph. Okay. Initially, it's decaying. And then at time 2, it jumps up by another e to the minus x. And then it decays from there. Like that, because it's a sum of 2 exponentials. So that is what this graph will look like. And this shows that the system initially, right, is, behave just like system 1, except at time x equals to 2, some amount of energy is being injected into the system, and then now it spikes up again. That. Okay. By the way, you can also graph these things using Desmos. So, for example, let's say you're interested in plotting this with Desmos. This is what you could do. Not that you get to use it on the exam, but say you want to. Say I delete these graphs. We can define our own unit step function. Now, the piecewise function, you use curly braces, and I say, okay, u of x, when x is greater than 0 is the function colon. I want it to be 1, comma. Otherwise, I want to be 0. Okay. So that is this function. Do you see that this can change the color to this? You see, that's the unit step function right there. All right. And what happens if I do this? E to the negative x plus e to the negative quantity x minus 2 times u of x minus 2. Okay, so you see that it's initially decaying as a e to the minus x, and at 2, another copy of e to the minus x is injected into the system and then decays like that. Right? So that is exactly what we expect. Okay, so at x equals to 2, some unit impulse of energy or whatnot, whatever y is being injected into the system. Okay, so that's kind of the interpretation of this delta x in a differential equation context. Okay, so let's actually do a little bit more just for funsies. How else can we interpret this delta x? So this is now remark time. Okay. Well, let's imagine the delta x, the unit step function again. Okay, this u of x, where it is 0 before 0, and it's 1 after 0. Now, this function, would you say it's differentiable at 0? Would you say it's differentiable? It's not differentiable, right? But if we were to assign a derivative, okay, then the derivative will be what? Well, the derivative will have to be something like it's 0 everywhere, but at 0, suddenly the slope is infinite, right? And then 0 again. So one can think of that the derivative of u, again, it's kind of nonsensical, is not really a function, is this delta of x, this delta function. And the amount of jump is 1. That means that, and that makes sense because the delta x function has a total area of 1, right? So the amount of jump from 0 to 1 is 1, so that's the area of delta x. So one can think of this thing like this, that the derivative of this unit step function is delta of x. So that's remark number 1. Okay, kind of bizarre, right? Remark number 2. Well, the Laplace transform of delta of x of p is a constant 1. This is an interesting Laplace transform. Does this 1 satisfy the behavior theorem? Behavior theorem. What's the behavior theorem? Do you remember? The behavior theorem says if the function, let's go back up. If the function is of exponential order and it is continuous at 0, or the area is finite near 0, and it's piecewise continuous, then the behavior theorem says that the limit of the Laplace transform at p goes to infinity should be 0, right? But 1 is a constant. As p goes to infinity, this doesn't go to 0, right? So this doesn't satisfy the behavior theorem. So one of these conditions is not right. Well, in fact, you can't really apply these conditions because this is not really a function, right? It's not really a function. And certainly, even though the integral kind of exists from 0 to epsilon, is it really piecewise continuous? Like, piecewise continuous means finitely many jumps of finite jumps. But this jump is sort of infinite. So it fails one of these 3 conditions. So we don't expect that it has this behavior that is a nice behavior, that the limit goes to 0. Okay, so that's kind of bizarre. But we can push this further. We figured out a function and we say that it's delta whose Laplace transform is 1. We can ask, is there a function whose Laplace transform is p, or is p squared, or p cubed, and so on? Now, for those functions, we don't have them yet in our table, but we're going to define them. So what we're going to do is we're going to calculate the derivative of the Laplace transform. Oh, and by the way, I may be going over time because since this is recording, I get to just say all my piece. So you can stay, but I'm going to continue. All right, it might take a while. So sorry, this might go extend for maybe another 30 minutes or so. But this is all going to be recorded. But let's consider the derivative of the delta function and consider the Laplace transform of that. Okay. So what would this be, right? What is this? Well, by our definition, well, our rules with the inside derivative rule, this equals to the negative delta of 0 plus p times the Laplace transform of delta of x, right? Okay, so this is the Laplace transform of the derivative of delta, if this even makes sense. Of course, it doesn't quite make sense, so we're going to make this a symbolic sense out of this. Immediately, we have a problem. What the heck is minus delta of 0? Well, earlier, didn't we define delta of 0 as infinity, right? But notice I put quotes around this infinity. It means that it's not really infinity. It's ill-defined. And here's mathematicians' way of dealing with this is, well, we're just gonna ignore it. We ignore it so it makes sense. Okay. Then, if we were to do that, because you cannot really have infinity, then this is just p times the Laplace transform of delta, which is 1. So this is just p. So here we go. Here is another rule. Is what would transform to p is this new gadget called the derivative of the delta function. Again, function in quotes, it's not really a function. So symbolically, it is this gadget, all right? Okay, can we go further, right? So what about the Laplace transform of delta prime prime? Okay. What is this? Let's see, let's use our rule. This is negative delta prime at 0, negative p of delta of 0, plus p squared of the Laplace transform of delta of x at p, right? And again, we come across these terms where it doesn't really make sense what they are. So what are we going to do? We're going to ignore them. That's right. So if we were to ignore them, then this have a very sensible quantity. Laplace transform of delta prime prime is p squared. So let's use 10,000 years of evolution. What do you think is the Laplace transform of delta to the nth derivative? Would you like to guess? If the Laplace transform of delta prime is p, Laplace transform of delta prime prime is p squared, yep. By ignoring terms, because we're going to need to calculate or determine what is the value of delta of various derivatives at 0, those are nonsensical, so we ignore them so it makes sense. In order for it to make sense, we define the Laplace transform of delta n to be p to the n. Okay, this is just, if we really want to figure out what function transforms to p to the n, it will be the nth derivative of the delta function. It's kind of bizarre, but that's how it goes. All right. And let me just add one more. Okay, let me just add one more, and this you can try to play the same game to verify. Also, since the Laplace transform of delta of x minus a is e to the minus pa when a is positive, we can also calculate the Laplace transform of delta to the nth derivative of x minus a. Now you can do this one by one. Nowadays, if you were to work it out, this you will get e to the minus pa times p to the n. Okay, so I will just put this in a box. All right. Okay, so this is this delta function. And again, its usage is when you have a differential equation, for example, these three equations, sometimes the driving force could be this unit impulse. Right? Okay, so here we have just delta x, it could be 7 delta x, 7 units, and then you will get a different solution. And to deal with these, you kind of have to use Laplace transform because these delta x functions only really make sense under an integral. So Laplace transform is the best thing to deal with this. You cannot use our exam 2 method really to solve this non-homogeneous term right here. Okay. All right. Okay. Sorry if I'm running over time, but it's all recorded. Let's talk about the last topic, which is convolution and this theorem called convolution theorem. Okay. So this is the operation called star. So we're going to figure out what does this mean. F star G. Okay. So I know that sometimes we on the computer we write the star to represent what? Represent multiplication, right? Well, here we're going to reserve this star symbol for this idea called convolution. All right, this idea called convolution. If you have a habit of writing star for actual regular multiplication, then I recommend you just write, draw a little star like that. Okay, so it's a new operation. The result of f star g is going to be yet another function. All right, and what exactly is f star g? So loosely speaking, f star g is a kind of blurring or blending, or blurring. Let's say this f star g of the function f of x and g of x. So it's kind of like you're mixing this function f and this function called g. By the way, do you know that your phone does convolution in some situations? In fact, you all know this word. On Instagram, when people say, oh, people take a picture on Instagram, right? And you say, this person looks so beautiful because they use their what? Do you know? They use what is the word to manipulate a picture? They use a filter. In fact, filter is just doing convolution. You take an image f and you take a filter function g and you compute this thing called f star g and you create this filtering effect, actually, whether this is blurring or blending or whatever, Gaussian blur or whatnot. So, on Photoshop, all these filters is really some discrete version of convolution, actually. So it really is just this operation. Now, on the computer, digitally, that's a discrete type of convolution. Here, we're doing a continuous convolution. So here's our definition. Okay. The definition is this, that the effect of convolution of two functions, let's say f star g, it is a function of x, okay? It's a function of x, is given by the integral t going from 0 to x of f of t times g of x minus t dt. So you take a function and you integrate against another function, but the other function is delayed by time t. And you integrate from t from 0 to x. The result is going to be a function of x, and that is defined to be the convolution of f and g. Okay. So let me box this. This is the definition. It's an integral again. And we're going to see why we care about this. But before we see why we care, let's see an example. Let's try to calculate the convolution of x with x. Okay, I hope we can see the difference. This is x, this is a star. Okay, star. Okay. What is the convolution of x star x? Okay. All right, let's try to apply our definition. This is equal to, it's going to be a function of x. So I will write the function of x. It goes from t equal to 0 to x of what? Well, my first function, this is my f of x. This second function, that is my g of x. So first we need f of t. So what's f of t? F of t is just t, right? Because f of x is x, so f of t is t. Times g of x minus t. Well, g of x is x, so g of x minus t is just x minus t, dt. Okay. What is this thing? This is tx minus t squared dt. Well, that's not a hard integral. This is just, well, let's see, we're integrating with respect to t. So x's are just constants. So the first one integrates to t squared x over 2 minus t cubed over 3, evaluated from 0 to x. And if we actually work that out, we get, plug in x, we get x cubed over 2 minus x cubed over 3. And when I plug in t equal to 0, everything is just 0, so we just get this x cubed over 2 minus x cubed over 3. This is x cubed over what? This is x cubed over 6, right? 1/2 minus 1/3 is 1/6. So, x star x, obviously, it's not quite clear why. It's x cubed over 6. Do you see? So it's not x times x, it's not x squared, it's x cubed over 6. Okay. That's kind of bizarre, right? So what would you like to know now? If I say x star x is x cubed over 6, what would you like to know? Well, what is, say, for example, x cubed star x to the 4th, right? So what is that? Okay, so generally, what's going on? So, what is x to the 3rd star x to the 4th? Now, of course, we could always use the definition of convolution, which is f of t times g of x minus t. But this is gonna be a little bit of work because this is f, this is g. So the definition, by definition, x cubed star x to the 4th is equal to the integral t from 0 to x of t cubed times x minus t to the 4th dt. Ugh. It's not impossible. It's just annoying. It's like, okay. Not impossible, but I kind of don't want to do it, right? But of course, you can do it, right? What is it? So we're going to figure out a smarter way to do this. Okay. Okay. We can do it smartly. Well, by a theorem, by another theorem, shall we say. Let me show you. Theorem. Okay. And this theorem is called convolution theorem. Okay, so let me write that down. So what does convolution theorem says? It says that the Laplace transform of the convolution of two functions f star g is simply equal to the Laplace transform of f times the Laplace transform of g. That's convolution theorem. That the product of two Laplace transform is the Laplace transform of their convolution. Okay, this is kind of amazing. This basically gives us some kind of product rule for Laplace transforms. That Laplace transform of a convolution is the product of their Laplace transforms. So this is why we use this notation star. It mimics multiplication, but not really, but kind of, right? So let's say we believe this. Let's say we believe this, okay? Let's say we believe this, and let's calculate what is the convolution of x cubed star x to the 4th, all right? So let's believe it for now. Let's use it to figure out what is x cubed star x to the 4th. Okay. So how we're gonna do it is this. Convolution only behaves nicely inside a Laplace transform. So we're gonna stick this thing into a Laplace transform to see what we get. So I say, notice the Laplace transform of x cubed star x to the 4th as a function of p, by the convolution theorem, it is equal to what? It is equal to the Laplace transform of x cubed times the Laplace transform of x to the fourth, right? Now, convolution theorem, you may abbreviate it at CT. So I'm using convolution theorem here, okay? So far, so good, right? Now, we know the Laplace transform of x cubed and the Laplace transform of x to the fourth. Laplace transform of x cubed is what? If you can type into the chat, hopefully you remember. X cubed has a transform of 3 factorial over p to the fourth, right? Times Laplace transform of x to the fourth is 4 factorial divided by the p to the fifth, right? So hopefully these are things you remember. This is equal to 3 factorial times 4 factorial times 1 over p to the 9th power. This looks like the Laplace transform of another polynomial. Of what? Well, kind of. The Laplace transform of x to the what power might give something like this. X to the 8th, right? But we have to be careful with our factors. Laplace transform of x to the 8th is 8 factorial over p to the 9th. So 1 over p to the 9th is really 1 over 8 factorial of x to the 8th, right? That's what it transforms from. So again, what I could do is I can just make my life easier. This is 3 factorial times 4 factorial divided by 8 factorial times 8 factorial over p to the 9th. So we see that, aha, this is 3 factorial, 4 factorial over 8 factorial, Laplace transform x to the 8th. So, conclusion. X cubed star x to the 4th is equal to 3 factorial, 4 factorial over 8 factorial times x to the 8th. Wow. So, done by convolution theorem, okay? You could integrate, of course. You could carry out this integration, which is the definition of convolution. But using convolution theorem, we compute what the Laplace transform would be and figure out what function would transform to that. Now, this, of course, has to assume that transforms are kind of one-to-one, but for our purposes, they aren't. So there we have it. The convolution of x cubed and x fourth is this number. Of course, you can simplify this to something. If you simplify it, what is this? 3 times 2 times 4 times 3 times 2 divided by 8 times 7 times 6 times 5 times 4 times 3 times 2, x to the 8th. What cancels? 3, 2, and 6, 4, 2, and 8, 3, and 3. 7 times 5 times 4 times 2. 7 times 5 times 4 times 2. What's that? 7 times 5 times 4 times 2. Is that 280? I think that's 280. This is 1 over 280. Sure, why not? You could also, of course, just leave it in the factorial. That's what it is. Okay. So far, so good. Let's calculate another convolution, just for kicks. Okay. Let's say we want to find some function f of x such that its transform is equal to, what about 1 over p times p squared plus 1? Okay. Now, wait a second. Do you recognize this? This is 1 over p times something, right? 1 over p times something. We have an integral rule about this. So we could solve this in a different way, right? Right? Earlier, we actually did something like that, right? I believe. Did we? Oh, we have something else. 1 over p times 1 over p minus 1. But instead of using the integral rule, we can recognize this as the convolution of two functions, right? So let's see, how do we use that? So the Laplace transform of f is the product of 1 over p times 1 over p squared plus 1, which is, well, the Laplace transform of something times the Laplace transform of something else. In the chat, can you tell me what transforms to 1 over p? 1 over p. What transforms to 1 over p? It is what? It is 1. Excellent. Now, for imaginary stickers, what transform to 1 over p squared plus 1? 1 over p squared plus 1, what transform to that? It is sine of x. Yes. Okay. A plus for now. Well, this is a product of two Laplace transforms. So, by the convolution theorem, product of Laplace transform becomes Laplace transform of convolutions. This is a Laplace transform of the convolution of 1 with sine of x. Aha. Aha, you say. This means that our function f of x is simply the convolution of 1 with sine of x. Okay, this is not 1 times x, this is 1 convolute with sine of x. Now, we should calculate what this is, okay? We need to calculate what this is. Okay, of course, this is intermediate answer, but what is this? Let's calculate this. Before I calculate this, let me give you some rules of convolution that will help us calculate this a little bit. Just a little bit. So let me write it on the side here. Here are some rules for convolution. Okay? And these rules are very easy to remember because they mimic rules for multiplication. So first rule is this, that the convolution of f and g is g with f. So in algebra, what would you say convolution is? If f star g is g star f, then we say star is, do you remember a word that describes this? Star is what? Is commutative. Commutative, exactly. Star is commutative. That you can do f star g or g star f, it doesn't matter. Now, I'm not going to prove it, but that really just comes from the definition of how this integral is defined. As it turns out, this integral, you can switch t with f and g by doing a change of variables. The change of variable being, x minus t equals u, and then you will get the other way around. It's very easy. So I'm not going to prove it, but it is commutative. Okay. 2. Star has another property. Well, star looks like multiplication, right? So what should we expect for f star quantity g plus h? Well, this is exactly what you expect. This is f star g plus f star h. So here we say that star distributes over sum. It's kind of like multiplication. Star is distributive. Property number 3. Property number 3, it gets better. In multiplication, this star also shares something with multiplication. It goes like this. F star of g quantity star h is equal to f star quantity g star h. Ooh. Do you know what this is called? If f star g star h it doesn't matter, do I parenthesize the first two of the star or the second two of the star? This is associative. Star is associative. Okay. And even though I write it in this corner, these are very useful properties. Okay. And for last one, well, any functions start with 0, convolving with 0. Would you like to guess what do we get? If we convolve with 0, let's think. If one of the function is 0, let's go back to the definition of convolution. If either f or g is 0, what should the integral be? It would be 0, exactly. So f star 0 is just 0. This is, there's no name for this. It dies to 0. This is kind of nice. Okay. So we have these basic rules. Again, the proofs are not too hard, so I'm not going to prove it. It's just applying the definition. You'll see they fall off very easily. But why do I mention this one right here? It's because to calculate 1 star sine x, I could calculate sine x star 1. Okay. It's just because in this definition, it's easier to use for the convolution. This is our f, this is our g. So remember, when we integrate this, the first function is just f of t, but the second function, you got to plug in x minus t, which is kind of annoying. But if g is just 1, then the second function is just always 1. So that makes it nice. That's why I put the 1 on the second position here. So in this case, by the definition, this is t from 0 to x. And by the way, you have to be careful with the bounds. Sine of t times 1, because g at t minus x is always going to be at 1. It's a constant function 1. dt, we know what integrates the sine, which is negative cosine of t, evaluated from 0 to x. So, what is this? This is minus cosine of x. Minus cosine 0 makes it plus 1. Therefore, final answer, the function f is minus cosine of x plus 1 by convolution theorem. So this is what gives this, okay? Now, just as a remark, there's many ways to solve this, many ways to do this. Okay, you could also do partial fraction and solve it. By partial fraction, we know it's going to be something of the form 1 over p, a over p, plus b over p squared plus 1. So we also expect that some sort of cosine and constant, right? So we have this. Okay. All right. Let's see one more example of this, and then maybe we'll call it a day. One more example. Let's do orange. Okay, so this is where convolution may shine. But again, there's many ways to do the same thing. Find a function such that its Laplace transform. Here I gave you, 1 over p times p squared plus 1. What about 1 over p squared plus 1 quantity squared? Oh, goodness. Okay. So how do we do this, right? How do we do this? Well, if the transform of f is 1 over p squared plus 1 quantity squared, that is 1 over p squared plus 1 times 1 over p squared plus 1, right? So far, so good? And 1 over p squared plus 1 come from the transform of what? They come from the transform of sine of x again, And both of them are like that, right? So we know that this is, by convolution theorem, the transform of sine star sine. So the function f is equal to the convolution of sine with sine. Okay. Now this time we cannot use the trick of one of them is 1 to make our integral nice. So we just have to bite the bullet to calculate this. So let's calculate. T going from 0 to x of the first function at t, so sine of t, times the second function at what? At x minus t. That's the definition of convolution of two functions. dt. So we now need to calculate the integral of this product of two sines. Now, this is the part where we have to know what is sine A times sine B. Do people remember what that is? That trig identity? Ooh. So let me write it over here.
1/2 cosine of something minus cosine of something.
Very good. Again, at gunpoint, you can figure out by Euler identity, using Euler's identity. You can definitely figure all these out. But just to remind you, sine A, sine B is equal to 1/2 of cosine of A minus B minus cosine of A plus B. Okay. You can derive it from Euler. So, say we believe this. Say we remember that. This is 0 to x of, okay, let's see, 1/2 cosine of A, which is t, minus B, x minus t, minus cosine of A plus B dt. 1/2 comes out, t from 0 to x, cosine of t minus x minus t, that is cosine of 2t minus x, minus t plus x minus t, that's cosine of x, dt. Just integration. Again, as I threatened you many times, this is simply a class of integration sometimes. And we know how to integrate all of this, right? Cosine of 2t minus x, the antiderivative is, of course, sine of 2t minus x divided by 2. And the derivative of sine of 2t minus x becomes cosine of 2t minus x, but the 2 comes out, cancel the 2, we get cosine. Minus, what's the antiderivative, very careful, of cosine of x with respect to t? Cosine of x is a constant in this integration. So this is just t cosine of x, evaluated from 0 to x. Compute. Plug in x, we get sine of x over 2 here, minus x cosine of x. Plug in t equal to 0, we get minus sine of minus x divided by 2, minus plus t equal to 0, that's 0. So you can check my work later. Sine of minus of x, that is negative sine of x, with a double negative, that becomes plus. Adding to the first sine of x, that's just sine of x. So overall, we get 1/2 sine of x minus x cosine of x. Bang. So that is the function f. That is a function who transforms to this thing right here. Okay, this is f. Wow. Okay. So you can use convolution to figure out, what is the inverse transform. That's sort of one of the usage of this. Okay. So very lastly, just very last point I want to make. Let's just prove convolution theorem very quickly. Again, the convolution theorem is integrals, right? So inside here, there's an integral. The Laplace transform is another integral. So here we're going to have a double integral. So the proof of this, if you were to make a guess of the theme today, anytime we have a double integral and there is a result, we're going to use multivariable calculus and interchange the order of integration. Again, if you don't know that, it's okay. I'm just going to do it just for record. Okay. So proof of convolution theorem. We're going to interchange the order to get stuff. Here we go. So the Laplace transform of, let's say, where should we start? Let's start with the product. F of x times g of x of p. By the definition, oh, sorry, not F, oh, sorry, I don't want to start with the product of the transform, sorry. So this times this of p. So the transform of f times the transform of g, okay? So what do we get? Well, the first transform, I can write it as x going from 0 to infinity of e to the minus px, f of x dx, right? We use our definition. Now, we're going to use a trick here. Instead of using x for the second one, I'm going to use a new dummy variable, say y. Okay, kind of familiar. And this I write g of y dy. Okay. Now, currently, my domain of integration is this upper first quadrant right here. If you write this as x, as y, this is this area integration here. We're integrating over that region, right? X from 0 to infinity, and y from 0 to infinity of e to the minus p times quantity x plus y, f of x, g of y, dy dx. That is this region. What we want is I'm going to do it into order change. But if I change the order of y, x, and y, it does nothing, right? It's just, they're the same. They're completely symmetric. So to break the symmetry, so this is trickery, mathematical trickery. To break the symmetry, because if I just exchange this order, it does nothing. I get back the same problem. So to break the symmetry, I'm going to let, let's say, x plus y equal to a new variable. Let's call it t. Okay. And I'm going to operate that in the inner integral. So that means x is fixed. Okay, again, this I'm just going to write math 11 warning sign. Let's see what happens. If I fix x, when y is 0, t is just x. And when y is infinity, t is infinity. X plus y, that is also known as t now. And x is fixed, so this is f of x. And y is simply t minus x. Okay, and dt here, let's calculate that. Dt is just dy. X is fixed. And we have dx. So now we have this integral. Now this we can break the symmetry, because now the region that we're integrating is no longer a symmetric first quadrant anymore, but rather it looks like this. Let me write t up here, x here. When x is fixed, t go from x to infinity. So what this looks like is this. This line is t equals to x. So it goes from t equals to x to infinity, right? So we're integrating along this region, going up like this. Okay, this axis is t. So if I were to interchange this order, okay, a little bit math 11, you can not listen if it's okay, but good to know. If I were to switch the order so that t is outside, now t wants to go from 0 to infinity as well, because if you project onto the axis t, t goes from 0 to infinity. But what does x run from? Well, x now run from 0 to t, right? 0 to t. So x going from 0 to t now. Okay. Inside, I still have the same e to the minus pt, f of x, g of t minus x, dx dt now. Okay. Inner integral is about x, so I can take out anything that has no x outside of this inner integral, which is the e to the minus pt. So this is integral t from 0 to infinity, e to the minus pt, integral x from 0 to t of f, well, fx, yes, it has x, g of t minus x, dx dt. Okay, so we have this. Now look at the thing in the parentheses. What does it look like? It looks like the definition of convolution, right? Except for convolution, didn't we write convolution as the integral of t from 0 to x, f of t of g of x minus t dt? But here, this is integral of x equal to 0 to t, f of x from g of t minus x dt, dx, right? So what is this? This is the convolution of f and g evaluated at t, right? Or what you could do is you can just switch the variables if you like, but here's what we're gonna do. For this entire expression, because it doesn't look as familiar, what we're gonna do is the following crazy thing, but not so crazy. We're gonna write all the t's, relabel as x, and all the x relabel as t. That's it. That doesn't harm anything. We're just doing relabeling. All the x, now write it as t. All the t, now write it as x. This is just changing what they look like, okay? So it's the same integral, right? The entire thing. So now this reads x from 0 to infinity, e to the minus px times the integral t from 0 to x, f of t, g of x minus t, dt, dx. Much nicer. Because this stuff in the middle, right here, this is indeed the Laplace transform of f convolute with g of x. And this is being multiplied by e to the minus px and integrate from x going from 0 to infinity, which is precisely the Laplace transform of something, of f star g. Done. Okay. So that's it. Okay. So again, it's just by integration trickery. And if you are going on to Math 11 or have taken Math 11, this is the type of trickery one can employ. Okay, I know I've been talking a lot. Above ends all of this. Let me put a box here. This is everything on the final. And that's it. Now, in terms of topics, that is, now, of course, you should still do some practice. And tomorrow I would do more examples of these things, so you get more familiar with this. But technically, this is all I would expect for you on the final topic-wise. Okay, so the last topics are convolution and convolution theorem, and the delta function business, integral rules with Laplace transform, and maybe some basic Laplace transforms, and how they interact with, differential equations. So that's the extent of the exam. Well, at least in terms of new topic. There will be old stuff, okay, on the exam as well. So you still want to review some of the first and second midterm material, at least the very basic things. But we can do more practice tomorrow and Wednesday. Okay, but that ends this lecture. In terms of topic-wise, this is all we are going to cover for the exam, up to this, plus old stuff. Okay? All right. So let me end the recording here. Let me just end the recording.